In the previous lecture, we discussed about the bandwidth of a QWT, that is the quarter wave transformer, and we saw that the QWT is essentially a very narrow band impedance matching transformer. And thereafter, we started the discussion on whether it is possible for us as RF engineers to improve the matching bandwidth that is offered by a QWT. So if you recall, when we plot the reflection coefficient magnitude versus the normalized frequency for a QWT, it looks something of this kind. So therefore, inherently, the range of frequencies over which the mod gamma is low, that is quite narrow. So therefore, as a first step to improve the bandwidth of a QWT, we decided to look at it in a slightly different way. That is, that the QWT has some arbitrary electrical length theta. This is what it looks like. So suppose this is my RF source. This is the main transmission line Z0. This is the matching transformer having impedance Z1, and there's a load ZL, which obviously has to be real, and the electrical length over here is theta. However, applying the quarter wave theory, Z1 is the geometric mean of Z0 and ZL. So if I now define that looking into the impedance transformer at the junction, the reflection coefficient is some gamma, then we define two partial reflection coefficients. One is gamma 0, the other is gamma L at each of the discontinuities. So we had proved in the previous lecture that this gamma would essentially be something like this. So what we saw was ultimately we are interested to make this gamma equal to 0 as much as possible. So therefore our focus should be on the numerator more than the denominator. So therefore, is there any way in which we can sort of make the denominator a lot more simple? That is not very difficult, because gamma 0 and gamma L by themselves have their magnitudes below 1 always, as we know. So therefore, the product of gamma 0 and gamma L would make the magnitude of that product even much more below 1. So therefore, there will come many times when the magnitude of this second term in the denominator can be very easily ignored, neglected, thereby making the denominator only 1. So therefore, to further solidify our approach, we have to ask ourselves whether can we make this gamma 0 and gamma L magnitudes much less than 1. Shall we try to achieve this? And how? So therefore, this discussion led us to something called as the theory of small reflections. That is, the gamma 0 and gamma L should be both very small, hence it is called as theory of small reflections. So if we apply this theory, then the gamma essentially reduces to something like this. So therefore, now it is a lot more simple, and you will very easily see that we can work with this with more ease as compared to anything else. So therefore, if we now take that expression for gamma that we have approximated, that is this, and we are essentially looking for a solution for this equation where this gamma expression essentially becomes 0. So this is possible when looking at the nature of the expression, we can say that one thing that we can very easily do is to make gamma 0 and gamma L is equal. And not just this, even if gamma 0 and gamma L are equal, it's not enough. We essentially need to make this plus sign turn into a minus sign, and that is only possible when theta becomes equal to any odd multiple of pi by 2. So let us say we will choose the first odd multiple, that is pi by 2. So I'll say both conditions are necessary. Both conditions are necessary. So now if this happens, what we essentially have is gamma 0 minus gamma L, and if the two are equal, the gamma essentially becomes 0. So therefore, this condition and also the fact that theta equals to pi by 2, what does this indicate? If theta is equal to pi by 2, that means the electrical length theta, which is also equal to beta L, that is equal to pi by 2. So therefore, as we know the value of theta, as we know what beta is, we can prove, and we have done this before, that L is equal to lambda by 4. So therefore, we come back to the condition for the quarter wave transformer, that indeed when theta becomes equal to lambda by 4, this becoming 0 is possible, or the L becoming equal to lambda by 4, not theta, the gamma will become 0. So therefore now, if I look at this in a converse way, suppose I have ensured somehow that gamma 0 is equal to gamma L, and I plot what is mod gamma as a function of theta rather than frequency, because as you know, theta can be represented in terms of length as well as beta, which is a wavelength or a frequency parameter. We have discussed this. So therefore, for this condition, when would mod gamma become equal to 0? It would become equal to 0 when theta becomes equal to pi by 2. So therefore, it would look something like this. Therefore, what we can say just by looking at this is that there exists one value of theta, at least in the range of 0 to pi. Let us say I'm plotting only in the range of 0 to pi. There exists one value of theta for which the gamma becomes 0. So therefore, this is called as a root or a minima. And as you know, this is exactly equal to what is the nature of the mod gamma versus theta for a quarter wave transformer. If you are not convinced, you can take a very small example. Let us say we want to match a line of impedance 50 ohms and we wish to have a load impedance 100 ohms. So therefore, the matching transformer needs to have the impedance, which is the geometric mean of the two, that is root of 5000, which is roughly about 70.71 ohms. Right? So having said this, we need to now see what would be gamma 0 and what would be gamma L. So as per definition, gamma 0 we have already defined, that is Z1 minus Z0 divided by Z1 plus Z0, and gamma L is ZL minus Z1 divided by ZL plus Z1. So if you substitute all of these three values in these two equations, guess what you will get? For gamma 0, you will get 0.1716. You can very quickly calculate and find out. And gamma L will also be equal to this value. So what we are seeing, interestingly, is that having Z1 as the geometric mean of the two by itself ensures that gamma 0 is equal to gamma L. So therefore, both this condition as well as the condition for theta, when you are meeting this condition for gamma, when you plot mod gamma as a function of theta, you will get it almost exactly equal to what we have already derived for a QWT. So therefore, if we are looking at this perspective, that is in the range of 0 to pi for theta, so this is what we're considering right now, because we know that beyond this it repeats. The question is, how about we try to have more values of theta for which mod gamma is as low as possible? That is, can we have more number of such roots or minimas? That's the question. In this interval, can we have more minimas? Well, say for example, if there are two minimas, it might look something like this. But the point is, the minima should be closely spaced. Because if the minimas again start moving away from each other, then between the two minimas, the value of gamma will increase. So therefore, this is indeed something which is very interesting to think about. So therefore, let us see whether it is indeed possible. Now the question is, what is the property of the transmission line, or what is the property of the impedance transformer that is causing this frequency response to have just one minima? Well, intuition tells me that there are two terms or two reflection coefficients, gamma 0 and gamma L, that is happening because of this single quarter wave transformer. So therefore, because of these two terms, we are getting one root or one minima. So therefore, if we somehow increase the number of reflection coefficients, if we increase the number of reflection coefficients in the gamma expression, intuition tells me that perhaps it may be possible. That may be possible. So therefore, let us now make a small modification in our impedance matching arrangement. This is our main transmission line Z0. Here we have our matching line Z1. But let us put another transmission line of impedance Z2 and then connect the load to it, ZL, which again is real. But the criteria is the electrical lengths of Z1 and Z2 are still theta. And if we now look at the gamma that is looking into the impedance transformer, then what would decide gamma? Obviously thetas are important. So we can define one partial reflection coefficient over here, that's gamma 0. Let us call this as now gamma 1 and this will be gamma L. So the way we derived the gamma expression for the QWT, that was from the bounce diagram. But if you try to draw a bounce diagram for this, it would be too lengthy. It's doable, but it's very time consuming. So therefore, if you apply the theory of small reflections here also, you can actually prove that gamma can be approximated, I should say approximated over here as gamma 0 plus gamma 1 times e raised to minus j2 theta plus gamma L e raised to minus j 4 theta. It is just an extension of what we had derived for the first case, the single quarter wave transformer. You can see the expressions are just extensions of this one. So one easy way to remember this is to look at each of the coefficients and multiply them with their effective phase for a round trip. So the round trip through only Z1 will take 2 theta. A round trip from this point till the load will take theta plus theta plus theta plus theta. That's 4 theta. So that's how it is. So then again, there are some things we need to look at. If we want to not run away from our quarter wave transformer theory, then if you remember, we had defined that this middle impedance Z1 is the geometric mean of the impedances on either end of it. So therefore Z1 is equal to the geometric mean of these two. So what we can say in this case is that Z1 will be the geometric mean of the two impedance at either end of it, that is Z0 and Z2. Likewise, Z2 will be the geometric mean of Z1 and ZL. And how do we define these individual reflection coefficients? Gamma 0, as you know, is Z1 minus Z0 divided by Z1 plus Z0. Gamma 1 now is equal to Z2 minus Z1 divided by Z1 plus Z0. And gamma L, that will be ZL minus Z2 divided by ZL plus Z2. So now the question is there any way to find out for what values of theta we can make gamma minimum? So therefore, one thing that we will try, just like the previous case, let's make gamma 0 equal to gamma 1 equal to gamma L. Let's make each of these individual gammas equal. So if we do this, it's not so easy to prove, but if we do this, you can either use calculus using theta as the derivative variable and find out for what values of theta gamma will be minimum. You can prove that gamma will be minimum in the 0 to pi interval when if theta takes two values, that is 0.325 pi and 0.675 pi. Right? So this is something very interesting. So now does it mean that if theta becomes some other value, the length should not be lambda by 4? No, not really. Because as you know, theta is beta L. And we can say beta is 2 pi by lambda. But I can always fix my length to some lambda 0 by 4. So therefore, if I now replace lambda with frequency, what I will get simply is pi f by 2f0, where f corresponds to lambda and lambda 0 corresponds to f0. This is the same one which we had derived for the case when we were finding out the bandwidth of the QWT. So what this means is, if I can fix the length as some lambda by 4 of each of these two lines, but the minima will now not occur when f by f0 is 1. So the minima will occur at some other values of f by f0. So therefore, we can actually find that out. For the QWT, the minima was occurring when f by f0 was 1. But in this case, when we have two transmission lines, you can actually make these two equal to this quantity. And you can find out what will be the value of f by f0 for which the gamma becomes minimum. You can find out, this implies that f by f0, if you equate these two, you will find that the value of f by f0 will be essentially twice of this, that is 0.65 and 1.35. Yes, 0.675 into 2 is 1.35. So in that case, what are we seeing? We are seeing that adding this second transmission line now gives us two minimas. And you can prove that these two minimas will not be exactly 0, but something very, very close to 0. So therefore, what this looks like now, if I now plot the mod gamma versus theta for an example, let us take the same example that we had taken. In the first case, where Z0 is 50 ohms and ZL is 100 ohms. So then in that case, you can very easily find out what is gamma 0, gamma 1 and gamma L. And for each of these cases, and you will see that essentially when you put the formulae for these two, you can find out what is Z1 and Z2. So you can take out your calculators and solve for Z1 and Z2. I have already solved for them. So we get Z1 is 62.99 ohms, almost 63 ohms, and Z2 is 79.37 ohms. So using this Z2, Z1, Z0 and ZL, you can easily find out what are these three values. You will again see that they are all the same, and that is equal to 0.1149. So now if I try to write the expression for gamma as a function of all of these, it will be something like this: 1149 times 1 plus e raised to minus j 2 theta plus e raised to minus j 4 theta. So if I now plot a graph of this theta versus mod gamma, you will see that the minimas will happen when theta becomes equal to these two values, 0.325 and 0.675 pi. So therefore one minima will be something less than pi by 2, the other minima will be somewhere over here. So therefore you can actually see that this is what will happen. So the maxima will again happen. This is 0. The maxima will again happen at pi. So what we are now seeing is that there are two minimas. There are two minimas. And our idea of increasing the bandwidth by increasing number of minimas seems to be working. Because as you can see, now the value of mod gamma is low for a larger range of theta or frequency. So only thing is, you can replace this theta by f by f0. Only these points will change, but the nature of the plot will not change. Now let us take one more example. Let's go one step further. Let us go for the case where we have three transmission lines between the main transmission line and the load. So therefore, let us say this is our main transmission line Z0. We have Z1. Then we have Z2. And then we have Z3 terminated by ZL, which again, as before, has to be real. And each of these lengths are all equal to theta. So we can define these partial reflection coefficients gamma 0, gamma 1, gamma 2, and this one will be gamma L. As per our approximations, trying to have this similar to the quarter wave transformers, each line impedance will be the geometric mean of the impedance at either ends. So therefore, Z1 will be the geometric mean of Z0 and Z2. Z2 will be the geometric mean of Z1 and Z3. Z3 will be the geometric mean of Z2 and ZL. The definitions of gamma 0, gamma 1, gamma 2, gamma L will be like what we have done. So in this case, if I now define the gamma, which is looking into the impedance transformer, which now is this complete thing. That will be equal to gamma 0 plus gamma 1 times e raised to minus j2 theta, again using the theory of small reflections. This is what it is going to be. Now the question is, what are the minima values of these? What are the points at which we can achieve a minimum in the gamma? So I can say, this is a little bit easier to calculate. You can prove that gamma will be minimum when, now in this case you will find three solutions. First is when theta is equal to pi by 4, next at pi by 2, and next at 3 pi by 4. So what we see is that now there are three minimas. Again, all the gammas must be equal. This condition does not change. All the individual gammas have to be equal. So then let us go back to that same example which we have been taking all this while. That is, Z0 is 50 ohms and ZL is 100 ohms. So if you put them into these three equations and if you solve for these three unknowns, you will get something like this. Z1 is 59.46 ohms, Z2 is 70.71 ohms, Z3 is 84.09 ohms. Notice something similar. Even in case when we had a single QWT, there was a 70.71 ohms there also. So now, using the Z1, Z2 and Z3 values and the Z0 and ZL values, each of these four gammas can be calculated. So therefore, you can again see that all of the gammas would be equal to each other, and that value precisely comes out to be 0.0864. So therefore, we can see that gamma using the previous expression would reduce to something like this. And again, if you plot mod gamma versus theta, you will see three minimas, as I was mentioning. One minima will be here. Here and here. This is pi by 4, pi by 2 and 3 pi by 4. Again, the maxima will be at pi. So this is something very, very interesting. We are seeing that as we add more and more number of transmission line sections or quarter wave sections, the bandwidth seems to increase. So thereby, this is one technique through which we can improve our matching bandwidth. But there are still several questions which are unanswered. The first unanswered question is, for a single quarter wave transformer, we know that theta must be equal to lambda by 4. Sorry, theta must be equal to pi by 2. Therefore, L has to be equal to lambda by 4. But for the cases of 2 and 3 transmission lines as matching sections, that lambda by 4 sort of seems to lose its value. Does it? Not really. So let us say, we take n is number of matching sections. Section means lines. So if n equals to 1, that is single QWT. We see the minima happens for theta equal to pi by 2. And we have already proved that this means L should be equal to lambda by 4. Very good. Now for n equals to 2, that is 2 lines or 2 sections, the theta values we derived for the minima are 0.325 pi and 0.625 pi. So as I said before, Suppose we say we are fixing the length. But if we fix the length now, what is happening? This means in case of n equal to 1, the single QWT, the minimum frequency will be when f becomes equal to f0. But if I say that L is fixed at some lambda by 0, lambda 0 by 4, which we are fixing, then in that case, what will be the frequency? Then in that case, what will be the frequency? So we have proved it that the minima will now no longer be at f0. Then in that case, the roots will be and these two. These are the minimas. Next, for n equal to 3, that is 3 lines or sections. What you see is what we derived, that is for theta, 3 values, pi by 4, pi by 2 and 3 pi by 4. So this is again if we fix L as lambda 0 by 4, that means the minima frequencies will now be what? You can simply substitute into beta L in this fashion and you will get the frequency is 0.5 f0, f0 as well as 1.5 f0. These are the minimas. So as the number of intermediate matching lines increase, the number of minimas also increase, which increases the bandwidth. How? By introducing more number of minimas. By introducing more number of minimas which are quite closely spaced. Increases 2. So the number of sections that you have, the number of roots you're going to have. So therefore, if you want more bandwidth, you have to increase the number of intermediate sections. Now let us look at one more thing. Let us look at one more point. Let us go make a table of n as one column. The other column is the individual gamma values of each section, that is gamma 0, etc., all the way till gamma L. So when n is equal to 1, that means a single quarter wave transformer, we saw that there are gamma 0 and gamma L which are both equal, and that is equal to 0.1716. When n became 2, we had 2 intermediate matching sections. What we saw was there are 3 reflection coefficients, gamma 0 equal to gamma 1 equals gamma L. and the value that came out was 0.1149. Then if there are 3 sections, then we saw that there are 4 coefficients, gamma 0, gamma 1, gamma 2 and gamma L, and all of them are equal to 0.0864. This is the case when Z0 is 50 ohms and ZL is 100 ohms. Just an example that we took. Do you notice something over here? You notice that as n is increased, what we are seeing is that the individual gamma is reducing. As n is increasing, the individual gamma between every 2 discontinuity is reducing. Why? Okay, before we go into the why, we have to ask, why is this important? Is the reduction having any value? This means that as the individual gamma is reducing, the discontinuity between individual line sections becomes lesser and lesser. That means the reflection coefficients are becoming smaller and smaller. What this means is the matching effectively is improving. Therefore, we can say that as n becomes larger and larger, the individual gamma values will reduce to such an extent that they may become almost 0. So in that case, that's the best possible case when we can expect a very, very, very large bandwidth from our matching transformer. Let us look at this from the impedance angle. Let us look at this from an impedance angle. So now let us make a table of n versus the Z values. Z values of intermediate lines. So when n was equal to 1, for the same example, the Z value was 70.71. For n equal to 2, there were 2 Z values. One was 62.99 and the other was 79.37. Third case, when n was equal to 3, the impedance value of the individual sections was 59.46, 70.71 and 84.09. So if you take these and look at these from a transmission line angle, for n equal to 1 case, our main line which was there was 50 ohms. Then comes our matching section, which is 70.71 ohms, and then our load, which is 100 ohms. You notice every discontinuity is like a step. Here we are at 50 ohms, then suddenly we are jumping to 70.71 ohm lines. So what's the difference? It's like 20.21 ohms. Then 70.71 we are jumping onto 100. So therefore this difference is something around almost 30 ohms. These two are quite big jumps. If I now look at n equal to 2, what is happening? This is my main line of 50 ohms. This is my first line, first matching section, then the second section, and finally the load. So this is 62.99, this is 79.37, So here, for the first jump, it's roughly about 12.99 ohms. The second jump is somewhere around 16.38 ohms. And the third jump is about 20 ohms. So if you compare this with the previous case, you will see that the individual jumps in impedance is much smaller as compared to before. Again, let us check n equal to 3. Ohms. I'm sorry. There has to be one more section for the load. This is 100 ohms. This was 59.46 ohms. This is 70.71 ohms. And this is 84.09 ohms. So the first jump is about 9.46 ohms. The second jump is about 11.25 ohms. The third jump is 13 point something ohms. And the fourth jump is 15.91 ohms. Again, as you notice, the jumps sizes are getting smaller and smaller. Therefore, just by the impedance values themselves, the matching is sort of becoming better and better. And that is why, because the jumps are getting smaller, the individual gammas, gamma 0, gamma 1 and whatever, they are becoming smaller and smaller. This is the very idea to do impedance matching for a broad range of frequencies. Reduce the discontinuity between two impedance values. And this is evident even in case of a single quarter wave transformer, where we saw the maxima in the mod gamma when you are plotting it as a function of normalized frequency. As the load and line impedances become further and further apart, the maxima in mod gamma increases. And as the line and load impedances come closer and closer, the mod gamma maxima reduces. So this is the very idea behind trying to achieve broader frequency range for the matching. The only drawback, as you can see, that you need to add a large number of sections, each of length lambda by 4, between the main line and the load if you want to get better bandwidth. And that is the sad part, because like in any other engineering problem, nothing in life is free. So therefore, if you want to obtain broader matching bandwidth, you have to sacrifice space and resources by adding more and more number of transmission lines between the main line and the load impedance. Now, using this example, or as an extension of this example, there exists something called as a Chebyshev matching transformer. Similar to this. This means what? This means the condition for the roots, or the conditions for the minima. Here what we saw was that all gammas are equal. Therefore, this is called as an equal gamma transformer. And very similar to this, there exists something called as a Chebyshev matching transformer. So, the Chebyshev equations are very complex and shall not be a part of this course. But I thought of explaining this phenomena to you using something a little more easy to handle, that is the equal gamma transformer, where all the individual reflection coefficients at individual junctions or discontinuities are all treated to be equal. This is not the only impedance transformer possible which provides better bandwidth. There is one more, and we shall discuss it in the upcoming lecture. Thank you.